Hi students, I am Praveen Sebastian Paul. In this lecture, we are discussing the exclusive OR gate or simply XOR gate. The exclusive OR logic function is a logic output 1 is obtained when only A is equal to 1 or when only B is equal to 1, but not both together at the same time, giving the binary inputs of 0, 1 or 1, 0, then the output will be 1. This type of gate is known as exclusive OR function, or more commonly an XOR function for a short. This is because its boolean expression excludes the OR both cases of x is equal to 1 when both a and b is equal to 1. In other words, the output of an exclusive OR gate only goes high when its two input terminals are at different logic levels with respect to each other. An odd number of logic 1s on its input gives a logic 1 at the output. These two inputs can be logic level 1 or at logic level 0, giving the boolean expression of Q is equal to A XOR B, which is equal to A bar dot B plus A dot B bar. The exclusive OR gate function, or XOR for short, is achieved by combining standard logic gates together to form more complex gate functions that are used exclusively in building arithmetic logic circuits, computational logic comparators, and error detection circuits. When we are considering the two-input logic XOR gates, the two-input logic XOR gate is basically a modulo 2 adder, since it gives the sum of two binary numbers and as a result are more complex in design than other basic type of logic gates. The truth table, the logic symbol, and the implementation of exclusive gate is shown here. Here in this figure we can see the two inputs, they are A and B, and the boolean expression is Q is equal to A XOR B, and it is read as A or B, but not both gives Q. According to the truth table, it is evident that 0 XOR 0 gives 0, 0 XOR 1 gives 1, 1 XOR 0 gives 1, and 1 XOR 1 gives 0. From the truth table, it is evident that the output will be high only for the odd number of inputs. The truth table shows that the output of an exclusive OR gate only goes high when both of its two input terminals are at different logic levels with respect to each other. If these two inputs A and B both at logic level 1 or both at logic level 0, then the output is 0, making the gate an odd but not even gate. In other words, the output is 1 when there are odd number of 1s in the input. This ability of exclusive OR gate to compare two logic levels and produce an output value depend upon the input condition is very useful in computational logic circuits, as it gives us the boolean expression of Q is equal to A XOR B, which is equal to A bar dot B plus A dot B bar. The logic function implemented by the two input XOR gate given as either A or B but not both will give an output at Q. In general, an XOR gate will give an output value of logic 1 only when there are odd number of 1s on the input to the gate. If the two numbers are equal, then the output is 0. If you are considering the three input logic XOR gates, an XOR function with more than two input is called an odd function or modulo 2 sum, not an XOR. This description can be expanded to apply to any number of individual inputs as shown in this truth table. Here the inputs are A, B and C, and the boolean expression is Q is equal to A XOR B XOR C, and it is read as any odd number of input gives Q, which simply means that 0 XOR 0 XOR 0 gives 0, 0 XOR 0 XOR 1 gives 1, 0 XOR 1 XOR 0 gives 1, 0 XOR 1 XOR 1 gives 0. Here in this case, we can see the two inputs are on high, therefore the output is 0. Similarly, the condition goes on. The symbol used to denote an X or odd function is slightly different to that of standard inclusive OR gate. The logic or Boolean expression given for a logic OR gate is that of logic addition, which is denoted by a standard plus sign. The symbol used to describe the Boolean expression of XOR function is a plus sign within a circle. This exclusive OR symbol also represents the mathematical direct sum of sub-object expression with the resulting symbol for XOR function. We said previously that XOR function is not a basic logic but a combination of different logic gates connected together. Using the two-input truth table, we can expand the XOR function to a plus b dot a dot b the whole bar, which means that we can realize this new expression using the following individual gates. That is, here in the circuit we can see a combinational logic. One of the main disadvantages of implementing the XOR function in this case is that it contains three different logic gates or NAND and finally AND within its design. One easier way to produce an XOR function from a single gate is to use our old favorite NAND gate as shown in this figure. The exclusive OR gates are used mainly to build circuits that perform arithmetic operation and calculation, especially adders and half adders, as they can provide a carry bit function or as a controlled inverter where one input passes the binary data and the other input is supplied with a control signal. The commonly available logic XOR gate and inverter IC are 7486 Code 2 input exclusive OR gate. So my dear students, in this lecture we have discussed the exclusive OR gate. In this type of logic gate, the output of an exclusive OR gate only gives high when its input terminals are at different logic levels or when its input are in an odd fashion, or simply the output will be high when and only when the inputs are in odd levels. So my dear students, hope you had understood this topic. So kindly go through this assignment questions. The question number 1 is write in detail about the XOR logic gate. Second one is write about the XOR gate equivalent circuit. And third one is explain the XOR function realization using NAND gate. So my dear students, in the upcoming lecture we will discuss the exclusive NOR gate or XNOR gate. So see you soon. Until then, goodbye, thank you and all the best.